Okay, I'll get started. The first thing I wanted to show you, just because was getting some emails and some questions about it. So if you go to, I think I went to Google, but you could also just go to the Scranton.edu site. Yeah, I Googled Scranton final exam schedule. So if you're wondering for your face-to-face classes, and I guess for your online classes when they are, here's the schedule. So I'll just point out ours. Ours is going to be on Tuesday, November 24th, right? Because that's our Tuesday, Thursday, 8:30 block. So block 19. So it's going to be 8 a.m. to 10 a.m. So we'll be here bright and early that day to take the final. Okay? Just a reminder, too, about the final, and I'll talk more about it as we get close to the end of the semester, and that's kind of upon us right now. We actually, including today, only have 5 classes left. Okay? So probably that last day on November 17th, I'll talk more about the final in terms of, what's the content going to be, how long is it going to be, but you will get the full 2 hours for that block to take that final exam. Okay? And the final is only worth a little bit more than a normal exam. So a normal exam is worth 15%. The final's going to be 20%. Okay? So I'll talk a little bit more about that on our last class. But there you have it, Tuesday, November 24th at 8 a.m. when it'll be in this room. All right, so last Thursday, we ended with you taking a quiz. So let me briefly go over this. So this quiz was on section 2.3 and section 2.4, lines and then functions. So this first question, I just gave you a slope and a coordinate, and you had to write me out the equation of a line in slope intercept form. So that means y equals mx plus b. So you just had to use the equation I'm giving you at the top of the quiz and plug in the values for x0 and y0. So I did see a lot of issues with folks plugging in a bunch of values for y and y0. So y and x in that equation, and I did cover that in the review that day, they have to remain there because our final equation for the line has to have that y and x variable. So once you plug in x0, y0, and m, you just have to solve it and then actually solve it for y, and that puts it in that y equals mx plus b form. So there's the first one. That was nothing special about it. The second one, b, because the slope was 0, the entire right side of the equation becomes 0, and then you just have y equals 4, right? Because it's a horizontal line if the slope is 0. So you had to have y equals 4. And then the last one, again, was just here's a slope and here's a point. Go ahead and write it out in slope-intercept form. And so they were each worth the point. All right, so the second one, more lines. So you had to, for this first one in A, I gave you 2 points now instead of just a slope and a point. So because you have 2 points, you can calculate the slope. So when you go ahead and do that, you get negative 1/2. And then you can choose any of the points to write the equation out. You'll get the same equation. I just chose to use negative 2 and 3. And again, you get y equals negative 1/2 x plus 2. Now, the biggest issues I've seen were with the parallel and perpendicular questions. So just to review, parallel means if 2 lines are parallel, their slopes are the same. So I gave you an equation, 6x plus 2y equals 12. And I'm saying that this line that I want you to write the equation of is parallel to that line. So what you have to do is put this 6x plus 2y equals 12 in slope-intercept form. So you'd get y equals negative 3x plus 6. So that means that slope is negative 3. So the equation of the line you're trying to write also has a slope of negative 3. You'll see that that's right here. And then the point the line passes through is negative 1, negative 2. And you go through that process and you get y equals negative 3x minus 5. That was B. Parallel lines, same slope. Perpendicular, okay, so same process here, except the relationship between perpendicular lines is not that they have the same slope, but that the lines are perpendicular. So there was this equation here, right? If you want to figure out the equation of one line that's perpendicular to another, you basically just take the reciprocal, so you divide one divided by the slope of the other line and tack on a negative sign. So again, this 10x plus 5y equals 1, put it in slope-intercept form, get a slope of negative 2. Plug negative 2 into this equation, and you end up getting 1/2, right? So what you'd be 1 over negative 2, which would give you negative 1/2, but then again, there's a negative sign there, so the negative signs cancel, and you get a positive 1/2. And then I gave you the point you go through slope-intercept form, all right? One of the things that's going to be super important, and it's why I had so many line questions on here, is that's something that you're going to use a lot in your business courses or in your psychology courses going forward. So it's important you understand at least the basic mathematics of a line. All right, so they were all section 2.3 questions. And I guess number 3 was as well. I was hoping this was kind of a gimme question. Here's an equation, and I'm saying to sketch the graph. So when you see x and a y in an equation, you should immediately think, okay, well, it's got to be a line because I don't have an x squared, I don't have a y squared, it's just x to the first and y to the first. Okay, so you could have put this in the slope-intercept form and graphed it that way, but I wanted you to do intercepts because that's another thing that's going to be super important. So to get the x-intercept, you plug y in as 0, solve for y. So you'd get 0, 4 for the y-intercept. For the x-intercept, you'd plug in y equals 0, you get x equals negative 3, so then that point's negative 3, 0. So to plot a line, you only need 2 coordinates. So why not use the x and y intercepts? So you'd plot negative 3, 0, and 0, 4 and just connect a line through them, and you're good to go. And now the last one, find the domain. So I gave you a square root function. So again, the thing underneath the radical, the radicand, has to be greater than or equal to 0. So in inequality form, you have x is greater than or equal to 4. So the interval notation, which is the important part of this question, you have a bracket 4, comma, positive infinity, and then a parenthesis. That's the domain. Now for the second one, it's a rational expression. Don't care about the numerator here because it's just a 2. But the denominator can't be 0. Otherwise, the function's undefined. So you had to factor that. That's just the difference between 2 squares. Solve each of those for, I basically say not equal to 0. So that means x can't be 2 or negative 2. But you have to write that in interval notation. So it's what you see there, right? It goes from negative infinity to negative 2, parenthesis, right? Because we're not including negative 2. And then between negative 2 and 2, and then from 2 to positive infinity. So that was section 2.4, right? That last question was the domain of a function. But we've been doing that, I don't know, all the way back someplace in chapter 1 we talked about domain. All right, so any questions about this quiz? So this was 2.3 and 2.4. For the folks that just came in, if you want to run up real quick, I can give you your quiz. So I saw Konstantinos, and then Angelo, you want to just run up real quick? So Konstantinos, here's yours. Anyone else? That's good. And Angelo. Here you go. Yeah. And I sent you an email this morning about later today. So check it, okay? Any other questions? Awesome. Okay. All right, so there was a homework assignment due today in the Dropbox. And again, I'm going to give you the opportunity I'm not going to look at it until tomorrow. So if you haven't uploaded it, go ahead and do that, right? Because it's just like free points on the exam, guys, right? So don't not hand it in, right? Because handing it in gets you points on the exam. So the homework was on section 2.5 and 2.6. So I'd like to go to 2.5 and ask if there are any questions about that section. So this was a section about properties of functions. So it was determining intervals for increasing and decreasing and an average rate of change. 65. So let's check it out. 65. Okay. Again, I'll put the homework at the bottom here. So 65 at the end of section 2.5. All right, so this one is find the average rate of change of the function as x changes from a to b. So right off the bat, we're looking at this, right? This is sort of the equation for slope, because that's actually kind of what we're doing, but it's just between two random points on a function. So what we say is, we said it's f of b minus f of a. So they're like the y values at 2 points b and a, and that's over b minus a. By the way, you'll be given this equation. You don't have to remember it, although it's pretty simple. Okay? So for this question 65, they say g of x is x cubed, and we're going from a equals -1 to b equals 3. All right? So now the f's in this equation here, remember, they're just placeholders for any variable. They could be h of x's, g of x's, like in this problem. Okay? So what I might want to do, I'm just down here, I'm going to find g of b, which is really g of 3. All right, so let's find that. So again, we're just plugging it into the function. So it's going to be 3 cubed. 3 times 3 times 3 gets you 27. And then I got to find g of a, and a is -1. So I get -1 cubed. So that's going to be a -1. All right? And we know what a and b are. Now we just have to plug these values in here. So instead of these f's being here, just for the sake of this problem, I'm going to change them to g's. So now that we know what all 4 values are, we could just put them into this equation to find the average rate of change. So g of b, we have 27, and we're going to subtract g of a, which is a -1, and it's going to be all over b minus a, so 3 minus a -1. So in the numerator, we get 28, denominator, we get 4, and the average rate of change would be 7. Okay? And again, you'll be given that equation. You just have to, plug the values into the function and understand what these 4 things mean, right? When you're reading a problem. All right, so that was average rate of change. Any other questions from 2.5? Yes, sir. 77. Okay. F of x, 2x squared plus 3x. Now what we want to do here is find the difference quotient. So here it is, f of x plus h minus f of x over h. Now what I showed you in class is this is really the average rate of change function, right? But we're assuming the x value, right, so here's like this is like f of a, and this is like f of b, but we're just saying that h value is such a small change, right? So when you actually look at the bottom and do b minus a, the x's go away. So that's why there's only an h there at the bottom. So we want to find that for this function, okay? So the first thing I like to do is, we have f of x, we have this part of the equation, but we have to find this part over here. So I'm going to do that off to the side. So instead of having x into this equation, I'm just going to plug in x plus h. So what does that look like in the next line? So 2 times, now instead of x, I have x plus h squared plus 3 times x plus h. So you see, everywhere I have an x, I just put in that binomial, x plus h. Now before I plug it into the difference quotient, I'm going to simplify this a little bit. All right, I'm going to leave the 2 here, and then I'm going to FOIL x plus h squared. You're going to get x squared plus 2xh plus h squared. And then again, distribute this 3. And then just distribute this 2. So it's going to look like this big, awful looking thing. And nothing cancels out. Okay, so you have all those terms there for f of x plus h. But now, it should be easy now to plug everything in. We know what f of x plus h is. We know what f of x is. We'll plug it in the difference quotient. So I'm going to put this big, long, ugly looking thing here for this first term, f of x plus h. So we have 2x squared plus 4xh plus 2h squared plus 3x plus 3h. I'm just going to put that in parentheses just so you understand that's coming from here. Now I'm subtracting the original function. Again, I'll put those in parentheses because we're going to have to distribute that -1. And the original function is 2x squared plus 3x and then all over h. Okay, so are there things going to cancel from this equation? Well, do you see how we're going to have negative 2x and then we have a positive 2x? So they're going to cancel to be 0, so we can forget about those. And I think the same thing happens here with 3x, and then this is going to be negative 3x. They're also going to be zeroed out. And here's what we're left with. We're left with 4, let's see, h, what am I writing down here? 4xh plus 2h squared plus 3h all over h. This is typical when you're doing a difference quotient, that the terms that remain all have that h value in them. So now we can cancel out 1h from each term in the numerator and be left with 4x, the h, because like these h's would cancel, plus 2h plus 3. So that would be our final answer for the difference quotient. Okay? So you might have an h left over, you might not. That's fine. Now, what is this giving you? Well, I had mentioned the other day that calculus-wise, you would use this to find the derivative of a function, which all that it means is the derivative of a function gives you a function that describes the slope at any location x. So in this case, it would be 4x plus 3 because that h term would disappear when you did the calculus part. So 4x plus 3 describes the slope at any location of this function, which is super useful when you're trying to analyze a function. But we don't have to worry about that so much here. We just have to practice making that difference quotient. Okay? All right, anything else from 2.5? I think that was pretty much it from this section, right? I think there might have been, yeah, just other than like finding intervals of increase and decrease, but that's pretty easy, and finding relative mins and maxes, not a big deal. All right, 2.6 was the other, yes? 2.5? Oh, okay. 2.6 was library functions. Now, I think we only looked at linear functions and piecewise. So what was your question, Bridget? 19. So let's see what we got. Oh, so I'm going to go back to section 2.6 here in the notes. And this is number 19. All right, so what do we have? We have a piecewise function, and here it is. Okay, so we want to find F1, F2, and F3. Okay, that's part A. All right, so F1, how do we know which one to do? Well, you look at the intervals. So where is 1 located? Well, that would be here, where x is less than 2. So f of 1 is 2. Okay? F of 2. So f of 2, which piece of the function would you use? Well, I would use the top one, right? Which, again, would just be whatever x is, right? So that would be a 2. And then finally, f of 3, again, that's greater than equal to 2, so it's whatever x is, so you get 3. Okay? So we found those. And then we want to sketch the graph. So I'm going to just do a terrible looking set of axes here, right? So we have x is horizontal, and then f of x, if you remember, is kind of like our y-axis. Okay, so it looks like when x is less than 2, so I'm going to mark 2, we're constantly at the value 2. But because it's less than for right now, I'm going to put an open circle there. I may fill it in when I look at the other piece of the function, but for now, we'll just leave it like that. And then it's just a line that's horizontal, right? Because if the y value is constantly 2, it's just going to be, going through the y-axis at 2 and go all the way to infinity. Now for x is greater than equal to 2, right? So we actually can get a point from this one here. It's 3, 3. So 3, 3. So we know there's a point here. And we know what f of x equals x look like. It's just a line with a slope of 1. But since this is x is greater than equal to 2, I'm actually going to fill in this circle because we could 2 is going to be a part of the function. And then that's what the graph would look like. Right? So really, I don't even need to have this solid circle here, but I had an open circle because you have to make sure that the other piece is going to fill it in, because it clearly, from the examples I went over last week, you don't necessarily fill them in. So, all right, so anything else from 2.6? Sir? 25. Okay, so we have g of x is 1 over x, and then we have another piece that's square root of x. And this first one is x is less than 0, and this one's x is greater than equal to 0. Perfect. And all we want to do is sketch the graph and then find its domain and range. Cool. Okay, so g of x is 1 over x. So let's look at that. So do you understand? It's good that it's x is less than 0, because you can't put 1 over 0, right? It would be undefined, okay? So let's just do a test value. What would happen if you plugged in, let's say, x equals 2, right? If you plugged in x equals, or g of 2, or negative 2, rather. Let's see what you would get. You'd get negative a half. So there's a point. Negative 2, negative a half. Awesome. So here's 1. So negative 2, negative a half will be right here. And let's do one more. I'm going to do g of negative 5. Okay. We get negative 1/5. So it's negative 5, negative 1/5. So which is bigger, negative 1/5 or negative 1/2? The 1/2 is bigger. So it looks like as you go more negative, you get closer and closer to the x-axis. And then as you get closer to the, I'm going to do negative 1, I get, let's see, 1 over negative 1, which is going to be negative 1. So that's right here. The closer you get to the y-axis, the bigger the value. So it kind of looks like this. It goes like off like that. And this goes all the way to infinity. All right, so that's that first part. Now the second part is the square root of x. And because that was on a quiz we took, right? We know what the square root of x looks like. But we're going to start at 0. So we know we have a point here. So g of 0 is just the square root of 0 or 0. So our first point's at the origin. And then let's do g of, just make some easy numbers. G of 4, that's the square root of 4, 2. So we have 4, 2. And that's probably all I need, because you know it's just going to careen off like this and eventually go off to infinity. Okay, so we want domain and range. So that was a tough one, right? Because maybe you didn't know what the 1 over x looked like. But now that we have the graph, we could do the domain and range. I must have bumped something again. Yeah. All right, so the domain. In terms of x values, it looks like if you go to the left, we're going all the way to negative infinity. We go all the way up to 0, but then 0 is there. So I think the domain here is negative infinity to positive infinity. Every x value results in an actual y coordinate. Range-wise, let's see. Well, we know we're going from negative infinity here. We go all the way up to 0, and 0 is a part of it, and then we go off to infinity with the square root in the y direction, so the range is the same. Okay. All right, anything else in 2.6? We're okay? All right, beautiful. Before we start section 2.7, I'm going to write this in the notes. That way even the people who are going to watch the video later that aren't here are going to hear the announcement. So our exam, right? Exam 3 is next Tuesday, November 10th. Okay, it's going to be only on sections 2.1 through 2.6. All right. So that section we just covered with piecewise functions, from that all the way back to 2.1, just because I look back at the other exams and we did about 6 sections apiece, right? So this is another 6-section exam, all right? So everything else I cover from this point forward is also just fair game for the final exam, okay? And again, I'll talk more about the final as we get closer to the end. So any questions about this exam? Just in terms of not necessarily the content, but is there anything confusing? It's 2.1 through 2.6. Okay, so I'm going to continue with some 2.7 today. On Thursday, I will reserve time, and I'll probably reserve time right at the beginning to cover an exam review to show you the types of questions that you should be worried about for exam 3. All right? Perfect. Okie doke. So let's get a different color here. Let's do maybe we'll go purple today. All right. So this is kind of a fun section, I think, maybe. It's graphing related, but it's not like you don't have to make tables and make it super precise. So section 2.7, I should make that thicker if I can. I don't know, that might be too thick. Is there a way to make it thicker somewhere on here? See what that looks like. You know what? We'll do with that. Fine. I just want you to be able to see it a little bit better up on the screen. So this section is titled Transformations. Okay. Now, before we actually get to the transformations, I'm going to define for you, and I think all of these, well, maybe the last one you might not, just some basic functions and what they look like when you graph them. Okay, so here's one you definitely know. F of x equals x, right? Why can't I write x? F of x is just a line, and this particular one just goes through the origin, and it has a slope of 1. So in this section, we're not super concerned with how perfect you draw everything. So here's for f of x. All right, everyone knows that function. Here's another one. F of x equals f squared, or x squared. What would we call that shape? Yeah, it's a parabola. Now this particular one starts at the origin. We call that the vertex of the parabola, and it just goes like this. Now notice I'm not worried about the coordinates of this, but I'm just drawing the general shape. Okay, that's f of x squared. Okay, here's another one. F of x is x cubed. All right, so this is a cubic function. Now this one's similar to a parabola, right? But so you're going to kind of have the same look of a parabola over here. It's a little steeper. But because you can plug in negative values when you're cubing something and you'll get negative results, instead of the parabola being up, this part being up here, it actually just goes below the negative x-axis. Okay? So hopefully you've seen those at some point before, all right? Now the two that you might not have used that often, but we did use one of these recently, actually just right now, today. We have f of x equals the square root of x. Now we know what that looks like. We just did it. It starts at the origin and then kind of careens off to negative and positive infinity and positive x, or positive infinity in the x and positive infinity in the y. And then finally, the only other one that we're going to concern ourselves with is that. That's the absolute value symbol around that x variable. Now that's similar to f of x equals x. So if I plugged in positive values for x, I'd get positive values, and it would look like this, right? I'm basically writing the same. It's this basic thing right here. I just rewrote it, okay? But because you're taking the absolute value, you can never get a negative value. So instead of having a line down here like f of x, you have a line going up like that matches the line on the right. Okay, so these 5 functions are the ones we're going to utilize in this section, okay? Again, 3 of them I know you've done in the past. The square root function we've been using here, and then the absolute value, I think this is the first time I've shown it to you, but you've probably also seen that one. So we're going to work with these. So what do I mean by a transformation? Well, I mean moving these functions around the coordinate plane and being able to identify how that works by looking at the equation and analyzing it. Okay, moving it around, stretching it, compressing it, flipping it. Okay, so there's all these different things we can do with them. So what I'll do is I'm going to walk through all these different types, and I'll use some of these functions as you go along, just to show you that you can use any one of them to practice, but some of them are easier than the others. Like the parabola, that's a real nice one to use, f of x equals x squared. So you'll see that a lot. Okay, so let's go ahead and start talking about the first transformation, and there will be 4 total types. The first one is the vertical shift. Okay, it's number 1. So this is a shift in the y, I'm going to call it dimension, right? Because it could be, I don't want to say y directions, because you might always think, well, that's up, right? But you could shift downward, okay? So if you had something like y equals f of x, okay? So this is just going to be an equation of a graph. If you started with that, and let's say for the example, well, the general way to describe a vertical shift is you're going to see y equals f of x, right? The same function is going to be there, but then you're going to be either adding or subtracting some value, c. So let's use a parabola to demonstrate this. So again, here's our starting function, f of x equals x squared. All right, I'll have it in orange. And you're drawing it the best you can. Okay, so now what my goal is, I want to look at g of x, which is x squared plus 2. Okay, so this is going to be a shift, a vertical shift. Now, what's nice about this is if the vertical shift is plus 2 is positive, then the entire function just goes upwards, so a vertical shift by 2 units. So if I were to graph this, we'll get the orange, I would just mark right here. And really, that would make sense if you were to analyze it like we've been before. Like, what would happen if you wanted to find the y-intercept, right? You'd plug in x equals 0, and what would you get? You'd get 2, right? So that's the y-intercept, and it happens to be the vertex of the parabola. So nothing changes with the parabola aside from we shifted it vertically. So you would just draw it the same way as before. So that's g of x. On the same graph, I'm going to do another one. I'll call it h of x. We'll say it's x squared minus 3. So what does that do? Well, we have, again, the x squared is the base function, the one we already know, and the negative 3 means we're going to vertically shift downward 3 units. So 1, 2, 3. Okay, so that's the vertex. And then I just draw the parabola like I would before. So you notice I'm trying to draw these parabolas to look the same because we're not changing, we're not widening the parabola, we're not shrinking it, we're not flipping it. All we're doing is moving it vertically up and down, all right? So when you have your base function and then you just have a plus whatever or a negative whatever after it, that's just a vertical shift. Okay? I'm hoping that is pretty simple and is making some sense. All right, so that's the first type. That's simple, easy. So if you could have a vertical shift, that must mean you could have our second type of transformation, the horizontal shift. Okay? The horizontal shift. All right, so if you had some function, let's say y equals f of x. So this f of x could be, again, a parabola, cubic, square root, whatever. Here's what it would look like. So for the vertical shift, it was the function and then plus or minus a number. Now, for the horizontal shift, it would have to be something like this. It would be the function, but instead of having x, you'd have x plus or minus c. So I'll show you what that looks like. Okay, so let's start with, I'm going to do the parabola again, because again, I think they're the easiest to see. So here's our parabola. Should have just copied it instead of writing it out every time, but what are you going to do? Here's our parabola to start. That's just our plain old function in our library. Now what I'm going to say is, all right, I'm going to do g of x is x plus 2 squared. Okay? So now you're seeing, instead of having the plus or minus number outside of the original function, we have to actually incorporate it. So instead of x squared, we have x plus 2 squared. Now, it's not a problem, it's just you have to think differently now from the vertical shift. If you had plus 2 in a vertical shift, that meant you go up 2, all right? When you have a negative 2 here, that means you're going to shift to the negative direction, so to the left. So let me get a set of axes here. All right, so here's going to be our x plus 2 squared. So that's a shift to the left. Now, we didn't do a vertical shift. We're only moving along the x-axis. So once your shift, your horizontal shift is finished, then you just draw the parabola like you would normally. So plus 2, this really means to the left 2 units. So you have to think opposite for vertical shift. So then if I had a function, h of x was x minus 5 squared, we know it's still a parabola, but we know it's now going to move to the right 5 units, right? Negative 5 means to the right 5 units from a normal parabola. So it's 1, 2, 3, 4, 5. And then you draw your parabola. Okay? So anywhere you would see an x in our original functions, so just to give you an idea, for like the square root, I won't leave this here, but if you did a horizontal shift for the square root, you'd have x like minus 2 or something underneath there. So we know that shifts to the right 2 units. But if you saw the square root of x minus 2, we would know that's that's not 2. The square root of x minus 2, that would be a vertical shift down, right? So it just depends on where you see these x variables in these equations. All right, so these are the 2 easiest, I think, vertical shift, horizontal shift. So what you can do is you can combine those. So let me show you just a real simple combining of these. I think I'll use, so I'm going to combine a horizontal and vertical shift. I think I'll use a different function. Let's see. Let's do, yeah, this will be going. Let's say there's a function, g of x, and it is the square root of x minus 1 plus 4. Okay? So if you saw something like this, you would know your base function is square root of x. So we know it looks like, I don't know what shape that is. This thing that careens off to the right, right? That's the square root of x. So we know we have to start with that base function. And from the look of it, we have to shift it to the right one, right? We're going to shift this. Let me show you, get in our color. This means we're going to go to the right a plus 1 unit. And then the plus 4 means we're going to go up plus 4 units from the origin and be able to do this. So here's what it would look like. All right, so I'm going to shift. I'm going to need some points here. I'm going to shift positive 1 and then shift plus 4. So essentially that's going to give me a point, right? That's telling us how we're going to shift the origin for this function. Now once we're there, we just draw the function out. So there you go. Boom. So there's the transformation. Yes?
Are we always going to be sketching these from the origin?
Well, you'll always have to start from the origin.
Yeah, that's what I mean.
You're always going to have one of these. It's only going to be these 5, and you're always starting with one of these, and it will be at the origin. Yes, correct. Okay. All right, so they're the first 2. Not terrible. Okay, I think they're fairly straightforward. All right, the next 2. This is number 3, called reflection. Okay. I'm going to define this for you as you're going to rotate. Rotate might not be the right word. Let's say this. It's going to be mirror the function across x-axis. Okay? So what does this look like? Well, if you had a y equals f of x, and you wanted to do a reflection transformation, this is simple. You just basically do negative f of x. So whatever your function was, you essentially multiply all the terms in that function by negative 1. That's pretty simple. All right? So I'm going to give you a couple different types here. So let's look at, again, we'll do a parabola. We like those. So here's what we're going to do. I'm going to put them all on the original graph here. So we have, here's a parabola. We'll call that g of x is x squared. And then we're going to I'll put a red function here, and we'll say, what do we want to do? Let's do a square root. Okay? So that's h of x is the square root of x. So we're always starting with the couple of those initial 5. So here's what we're going to do. I want to go ahead and do reflection. So I'll do that over here. Oh, that was terrible. That wasn't great either. There we go. Not bad. Okay, so what we're going to do is we're going to say, I'm going to pick a couple numbers here. We'll say L of x. I wanted to use orange. L of x is x squared, negative x squared. Okay. So all you have to do is think about the orange function, orange graph I have on the left, and flip it or rotate it across the x-axis. So all that would look like would be this. This origin location wouldn't change, but instead of all the values pointing in the positive direction, they're going to point in the negative direction. I drew that kind of not the same, so I just want to make sure they're a little fatter there. There you go. All right, so you see how I flipped it? We're going to do the same thing now with a new function n of x and say negative the square root of x. All right, so again, we're just flipping that across the x-axis. So again, our origin's staying the same, and then now I'm flipping it this way. All right, that's reflection. Just flipping it across. No biggie. All right, so that one's not bad. Any questions on that one? Great. Last one we're on, number 4. There's only 4. Okay, this one's stretching and compressing. Okay, so again, if you have a y equals f of x function and you want it to stretch. Now, stretch might not make sense to you, but I'm going to say really it's like widening. All right, we're going to widen. So I think a stretch is widen. So what does that look like? Okay, so we're going to put something in front of f of x. All right, and if we want to stretch it, it needs to be a value less than 1. So all I'm going to do is say, I'm going to call it a. And for stretching, a has to be less than 0. Okay? No, I'm sorry. It has to be between 0 and 1. So it has to be a decimal or a fraction. So here's an example. What if I had y equals x squared, and then I said, y of x is x squared, and I said g of x is 1/2 x squared. All right, so let's try to plot that. Okay, so here's your original. This is y equals x squared. So there's y of x. Now we want to do g of x. Now, you have to widen it, okay, which means you're stretching it along the x-axis. But how much you stretch it or widen it, that's not my concern. It's just, so if you were doing this, I would have to understand that you understood what it means to have a 1/2 x there. So if you'd have to do something like this. So because I'm widening it, I'd have to see it outside the bounds of the orange one, right? So does that make sense from widening, right? You're just making it, you're stretching it in the x direction, okay? That's widening. Now for compressing, think about it as shrink. All right, so if you had, again, y equals f of x, we're going to use the same one. Again, let's say you'd have b times f of x. Now, b would have to be greater than 1. So this would be putting numbers greater than 1 in front of the function. So I could do something like, all right, well, I'm going to say h of x is 2x squared. All right, so that means we're going to shrink it. All right, so you're referencing the orange graph here. So shrinking it would mean h of x would have to be inside of the orange. So you'd have to put something like here. And that would tell me you understood that having a 2 in front of that meant that you're shrinking it. So instead of widening it, you're shrinking it in the x direction. Okay. So there are the 4. The 4 transformations. Now, what could happen when you're doing these? It's possible that you're given a function that does all 4 of them at the same time. Okay? So that would be combining all of them. All right? But there's an order in which you need to do them. So there's an order. Okay? the first thing you should do is the horizontal shift. So get that out of the way first. Then you're going to do any stretching or compressing. Then you're going to do reflection. And then lastly is the vertical shift. Okay? And we're going to go ahead and do one of these examples. I mean, I don't know if you can remember, if you think about it as HSRV. I can't think of anything funny for that, but you know, if you like acronyms and you don't want to remember, then just make HSRV. So it could be like something recreational vehicle. Somebody give me something for HS. Any ideas? Yeah, I got nothing. I don't know. Just remember HSRV. So horizontal, stretching, reflecting, vertical shift. All right. So here is an equation. Now it'll look complicated, but we'll just dissect it as we do each transformation. So let's say we had y equals -1/2 times x plus 3 squared minus 4. There's a lot going on there, right? So this one has all 4. So let's kind of identify them. Well, the -4 at the end, that's a vertical shift downward. The plus 3, that's a horizontal shift to the negative direction. The 1/2 is a stretch. And then that negative sign is a reflection. Okay? So remember, HSRV. So the first thing we're going to do, and what's the base function on this one? Oh no, like of the 5 functions at the beginning, which one? This is clearly a what? It's not a line or a cubic. It's a parabola, so that's the shape we're working with. Okay, so let's do them in order. So I'm going to do H first. I'm going to do the horizontal shift first. Now, if you're like really good and you want to just go ahead and draw the final answer because you could do this, at the same time, hey, I'm okay with that. I'm going to do them step by step. So I'm going to do the horizontal shift, which is this, all right, the plus 3. So I know I'm going to start with a base parabola that is shifted to the left 3. And I'm just going to draw the parabola as if I only shifted it to the left 3. Okay, wonderful. The next thing is we're going to look at stretching and compressing. So we're going to take that same parabola, now that it has been shifted, 1, 2, 3. All right, we know it's here. All right, what does that -1/2 do? Well, up in our example, -1/2, since that's between 0 and 1, that's going to cause a widening of the function. So instead of it looking like how it does under the H, I'm just going to draw it a little wider. And again, that's going to tell me you understand that it widens. And you can even exaggerate it just so you know I'll be able to tell. So there's a very exaggerated parabola. So you see the difference. So there I just did stretching. The next thing is R, reflection. Okay? So here's our axis. I guess I'll go to blue this time. All right? So we know we're starting still over here at x equals -3. Now what is that? So the reflection part is this negative, right? That's the negative. Here I should circle the 1/2 so you can color code this later, right? So the red was the stretching, the orange was the plus 3, and then the negative sign is reflection. So what do? We take that parabola and we flip it across the x-axis. So again, the size of it stays exactly the same. So we have that pretty exaggerated wide parabola. And then the last thing we need to do is the vertical shift. And I'm going to have to get a different, I want maybe a green color here. All right, so green, what are we going to do? Well, we're going to do this, the -4. That means a vertical shift downward for 4. So we were already here at -3. Now we're going to shift downward 4. So we're at this point right here. And nothing else has changed. Now we just have this wide parabola reflected across the x-axis that has a wide berth, like that. So there's our final answer. Now, could you have went to this graph directly? Yeah, the more you practice at these, you absolutely could, right? You could just immediately go, okay, well, I'm shifting to the left. I'm going down 4. I got to stretch it and then reflect it. So, like, if that's something you want to do, that's absolutely fine. But I think it's kind of foolproof going through it this method because, you know, I don't know. I think it's easier. And then less mistakes. Plus, more work you give me, the better. All right? That makes sense? So HSRV, try to get that in your head. So that is the end of this section. So there's a homework assignment. I will not collect this today, or I will not collect this Thursday, because I'd like you to focus on the exam, but these really aren't that difficult. So this is end of section homework in 2.7. And that's, I'll find the page for you. And if you'd like to come up and take a picture of the problems, that's also fine with me. Come on. All right. We are looking at, I'm in the 37s. Okay. 278, I believe, is the page number. And there's not that many because you're going to be graphing things. So 37, 47, 49, 59, 63, 67, 75, 79, and yeah, that's it. So 8 of them. Simple. Boom. Okay. 2.7. So it's just, do you understand those 5 basic functions, how to draw them, and then just these 4 shifts. Pretty simple. Okay. All right. Let's continue. So we'll move on to 2.8. Remember, what we just did 2.7, and then what I'm doing now, that's not on the exam. It's just material that'll show up on the final. So this is section 2.8, and this is on combining functions and composite functions. Oh, I'm running out of room over there. There we go. Okay. So I'll be honest with you, this is actually pretty simple. I'm not sure why they didn't do this back in the introductory section with functions, but there you go. So I'm going to give you some mathematical operations. So like, these are all ones you already know, but we haven't done them with functions yet, right? You've added numbers together and you've added variables and it's all worked out fine, but you haven't added it for functions. So I think it's here just to show you that the mathematical operations really don't change for functions, which is kind of nice, right? So let me just talk through them, and they're so simple. Let's do sum. So this is, adding 2 things together. So it's also maybe they have it here just because the notation is not strange. It's just you've probably never seen it before. So if we wanted to add 2 functions, so let's say f of x plus g of x, okay, you can write that as f plus g of x, okay? So this is the notation functionally. All right, you wouldn't just see f of x plus g of x, you'd see that, okay? But that just means you're adding them together. That's easy. That's nothing, right? You just literally add whatever f of x is and g of x and simplify. All right, so sum, that's that. Difference. Okay, again, you won't see f of x minus g of x. You would see f minus g of x. And it just means you subtract g of x from f of x. Now, the problem you could run into is that negative sign means that whatever terms exist in g of x, that negative sign has to be distributed through each term. So you do the difference and then simplify. All right. So sum difference, right? We're just kind of going through the basic operations on the calculator. The next one I'll go talk about is product. So this would be, let's see, f of x times g of x. So sure, you can multiply two functions together, right? Like remember when we did FOIL, we had x plus 1 times x plus 3. Well, they could each be functions themselves, and we know how to do that. That's easy. But the notation for that is f, and then the multiplication symbol is sort of like a dot, a solid dot, and then g of x. So you just multiply the functions and simplify. And then finally, I'm not going to call it division, because really we're creating a quotient. Division implies we'll actually get a result when we divide the denominator into the numerator, but that's not the case here with functions. So this is if we had f of x over g of x, okay? And if you've guessed it, it's going to be f over g of x, all right? So really that's just to show you that there's some new functional notation for the basic mathematical operations. Okay. All right, so let's just go through a couple examples. These won't be too bad. They should be simple. Let's go with this light blue. Actually, you might not be able to see that. What is that green? Okay. So I'm going to give you a bunch of functions. All right, I'm going to give you f of x is x squared minus 4. I'm going to say g of x is x squared minus 6x plus 8. Okay, so two functions. And here's what we're going to do. We're going to compute a sum difference product and then a quotient, and then simplify once we're all done, and then also plug in values. So let's first find f plus g of x. Okay, so that just means we're going to add these together. So we have x squared minus 4 plus the quantity x squared minus 6x plus 8, but that plus quantity doesn't change anything in there. So now we just simplify. And we would get, let's see, we're going to have 2x squared minus 6x, and then negative 4 plus 8 is plus 4. All right. So we just summed those two functions together. So you might want, there might be questions where it says, all right, we also now want to find f plus g of 1. So what do you do there? Well, now that you know what f plus g of x is, you just plug in a 1. So you'd have 2 times 1 cubed minus 6 times 1 plus 4. And what do you get there? 2 minus 6 is negative 4 plus 4. Oh, you get 0. Okay. So that's a sum. All right. So that's sum. So now we can do difference. We'll do f minus g of x. So this is a difference. So we'll do, you start with the first function f, so x squared minus 4, and subtract g. So here's where I mentioned that you're going to have to distribute that negative sign through each term. And let's see what we'll get. So you see that the x squareds are going to cancel, right? Because you have x squared minus x squared. negative minus 6 times minus 6, so you're going to have 6x. And then negative 4 minus 8 is going to be negative 12. So this is something interesting to point out, but again, not in this class will you figure out why it's important. But let's say so these are f of x and g of x are polynomials of order 2, right? Polynomials of order 2. When you add them together, you still have a polynomial of order 2. But when you subtract them, you get a polynomial of order 1. Okay? So you get different functions from different types of functions from what you started with, which is interesting. And it's another calculus thing, but we're not worrying about that here. All right, let's do the super annoying one. Product. This one's going to suck for product. We're going to do f, a solid dot g of x. So this means we're going to multiply these things together. And when I made this example, I was trying to get the fact that you'd get a different type of function in difference, but then it made it so that we have to distribute this whole god-awful thing. All right, so let's just assume we're just going to distribute the x squared and everything. You get x to the 4th minus 6x cubed plus 8x squared minus 4x squared plus 24x minus 32. Holy smokes, look at that. Okay, so that's going to be, I'll just put it down here, x to the 4th minus 6x cubed plus 4x squared plus 24, oh, that was supposed to be an x up there, minus 32. All right, so assuming I did all that correct, there you go. So there's what the product is. So let's look at the product of 1. So we're just going to plug in 1 for all those values. So you have 1 to the 4th minus 6, 1 cubed, plus 4 times 1 squared, plus 24 times 1 minus 32. What is that? So it's 1 minus 6, negative 5. Negative 5 plus 4, negative 1. Negative 1 plus 24 is negative 23. Negative 23 minus 32 is negative 55. Maybe? Yeah, sure. Did I do that math right? Even if I didn't, that's the process, okay? I won't give you something crazy like that, so don't worry about it. Now, quotient. And this is where we'll end the day today after this. So let's say I had f of x over g of x, or no, I want to use the notation. F over g of x. All right, so f of x is x squared minus 4, and then g of x is x squared minus 6x plus 8. What you don't want to do is just say, oh, we're done, okay? You want to try to simplify. So this is, oh my gosh, this is like back in section P4, I think. You have to factor, might be P5. Yeah, it might be P5. Factor the numerator and the denominator, so that numerator is easy. It's x minus 2, x plus 2. And then can we factor this down here? X. So for 8, we can do 4 and 4, or is this possible? 2 and 4. I don't know why I was thinking that. 4 and 2. Yeah, and then negative signs. So what happens is we have an x minus 2 term in the numerator that can cancel with an x minus 2 term in the denominator, and we're left with x plus 2 over x minus 4. And again, if we wanted to find f over g of 1, we just plug in 1 for those x values. So 1 plus 2 over 1 minus 4. We get 3 over negative 3 or negative 1. So we literally are just using a little different notation, but doing the same things we've been doing all semester. Multiplying polynomials, looking at rational expressions, subtracting and adding polynomials together. So hopefully that's not too bad, just a little bit notation. Okay, so just before we pack up, I know today's election day. No matter what happens, I hope everyone just stays calm, right? You know, there's a lot of things, you know, when you watch the news, it's tough because, depending on the station you're watching, you're getting one side of a story versus some other station side. So just my advice would be, no matter what happens, just be kind to everyone. Like if you're a Republican and you want President Trump to win, if you're a Democrat and you want Vice President Biden to win, that shouldn't matter in terms of you interacting with other people. Okay, so just please be kind to everyone. All right, so if your candidate loses, just try to be, gracious and move on with the life, and we'll figure out what's going on. All right, folks, there you go. Have a good day, and I'll see you Thursday.